So we've learned a little bit about forest succession. First stage of succession, there's a natural disturbance, some event that clears away the existing forest, creates an opening through which light pours in. The first plants to grow in that first stage are plants that are sun-loving. They need lots of sun. They thrive in the sun. The first trees to appear in a western Douglas fir forest are the namesake trees, the Douglas firs. You see many stately Douglas firs in this shot here. Douglas firs are what is called a shade-intolerant tree. They need lots of sun to engage in photosynthesis. In fact, if you were to explore in some of the deeper reaches of this forest that are more shady, it would be hard for a young Douglas fir to survive. They need lots of sun. And as you can see, when they have lots of sun and nutrients available, they thrive and grow very quickly and get fat very fast. Photosynthesis is the process by which chlorophyll-containing cells in plants take available light, convert that to chemical energy in order to produce carbohydrates, namely glucose. Well, how do they do that? Well, they also take in CO2 and water. The main reason is that they want to produce glucose and carbohydrates. One of the byproducts also happens to be oxygen, which is valuable to us, of course. But it's important to remember that plants aren't doing this out of any sense of altruism. They couldn't care a lick about us. We just happen to reap the benefits of that other product produced via photosynthesis, that oxygen. But for the plant, the primary product is glucose, that carbohydrate, because it serves as a building block for their metabolism and also serves as a building block for a number of other products that are produced. One of those products is cellulose, which is the main building block for trees. And we'll talk more about the significance of cellulose as we talk about primary growth in a tree. So again, this is a Douglas fir forest. And as a Douglas fir forest matures, as the trees get taller, we have a canopy that starts to close. And even in the middle of the day, there's not as much sunlight as there would have been before. And as the canopy closes even further, conditions become even more shaded. Some plants are capable of photosynthesizing in very low light conditions. And one of those trees is what you see right here. This is a grand fir. It's a tree that is capable of photosynthesizing in very low light conditions. We call these trees shade tolerant, as opposed to the Douglas fir, which are shade intolerant plants. So we have a mixture of different tree species and different species that are capable of adjusting to different light conditions. You won't find many Douglas fir or shade intolerant trees on the floor of a shaded Douglas fir forest, but you'll find plenty of grand fir and other shade-tolerant plants, shade-tolerant trees such as western hemlock and western red cedar. So those are two definitions I think you should remember: shade-tolerant plants and shade-intolerant plants. Shade-tolerant plants are plants that can live and carry out photosynthesis in low light conditions. Shade-intolerant plants, like the Douglas fir you see here, are plants that are unable to live in low light conditions. They need full sun. So photosynthesis involves a race for the sun. The very top of the tree, called the leader, is racing towards the sunlight, trying to outcompete the other trees that may be located right next to it. Every year of a tree's growth is manifested in growth in height, but also growth in girth. So over the course of a year, trees get taller, but they also get fatter. As trees grow in height, that type of growth is called primary growth. As trees get fatter and they put on a layer of wood every year, that is called secondary growth. And that secondary growth is what we're going to investigate in a separate module as we investigate how to use an increment borer and how to determine a tree's age by investigating a core sample of wood. But more on that at a later time. We've just mentioned that every year of a tree's life manifests itself in growth in height, called primary growth, and growth in girth, called secondary growth. Now, those are two definitions I think you should remember. We have primary growth, which is growth in height at the top of the tree. The very top of the tree is called a leader. And primary growth also exists at the ends of the branches. Then we have secondary growth, which is growth along the trunk, the tree getting fatter. That type of growth emanates from what's called the vascular cambium. And we'll talk more about the vascular cambium a bit later. So we've just heard about primary growth and secondary growth. Primary growth is the tree getting taller. Secondary growth is the tree getting fatter. This huge Douglas fir here, obviously a big fat Douglas fir, if you were to take a look right inside the bark, you'd come upon a layer of rapidly dividing cells called the vascular cambium. The vascular cambium gives rise to two separate types of cells, phloem and xylem. Phloem on one side of the vascular cambium, the phloem tissue eventually differentiates and becomes the tree's bark. On the other side of the vascular cambium, you have what's called the xylem tissue. And that xylem tissue is what we will investigate in an open OSU module focusing on the increment borer and how to use algebra to figure out a tree's age. That vascular cambium gives rise to xylem, and those xylem cells change over the course of a growing season. They change in size, structure, and color. And the result of this differentiation in size, structure, and color results in different colored bands or rings on the interior of a tree. And those concentric circles, that xylem tissue, is what we will investigate as we determine a tree's age.
We've just learned that secondary growth is growth occurring along the trunk, emanating from the vascular cambium. Vascular cambium, what's that? The vascular cambium is a thin layer of rapidly dividing cells just inside the bark of a tree's trunk. The vascular cambium gives rise to two types of tissue, xylem tissue on the side facing the interior of the tree, and phloem tissue on the side facing the bark. Let's consider the xylem tissue a bit further. As a layer of xylem tissue is added to the tree over the course of a growing season, the xylem cells change in size, structure, and color. This results in two differently colored bands of xylem tissue. Those colored bands will represent 1 year of a tree's life. As those colored bands accumulate, counting them allows us to determine how old the tree is, its age. Indeed, as you can see here, looking at a tree trunk in cross-section reveals a series of concentric circles, alternating bands of light and dark-colored wood. Each of these circles is called a growth ring. Counting the growth rings allows us to determine a tree's age. A tree gets fatter, or puts on a new layer of wood, every year of its life. We can think of that new wood as essentially a layer of xylem tissue, which again is produced by the tree's vascular cambium. At first, when growing conditions are ideal early in the year, the xylem tissue cells are rather large, cell walls are thin, and the cells are light in color overall. We call this light-colored xylem tissue early wood. Then, later in the year, as a tree's metabolism slows a bit, the growth slows down. Xylem is still being produced, but now the cells are smaller, cell walls are thicker, and the cells appear darker in color overall. We call this dark-colored xylem tissue late wood. Taken together then, 1 year of a tree's life, one growth ring, consists of a band of light-colored early wood and a band of dark-colored late wood. A ring of light-colored wood next to a ring of dark-colored wood. Again, if you were to magically look inside a tree and count either the dark-colored bands or the light-colored bands, you'd be able to determine the tree's age. As we'll learn, when determining a tree's age using an increment borer, we will be looking at yearly changes to the xylem tissue. Now, what do we mean by changes to the xylem tissue?
As a tree puts on a new layer of growth every year, you can think of that growth as forming concentric circles within the tree. The tree puts on new wood in the form of xylem tissue that emanates from the vascular cambium. The vascular cambium would exist right inside the bark of the tree, a very thin layer of tissue, not any thicker than a few pages in your typical paperback novel. So the vascular cambium will produce xylem cells, and those xylem cells will form a new layer of wood that's put on every single year. It exists as concentric circles because as the new wood is put on throughout the year, the cells differentiate. Early in the growing season, the xylem cells are larger, but the cell walls are thinner and they are lighter in color. So there's a layer of light colored wood. Then later in the year, as metabolism of the tree slows down, the growth starts to slow down and those xylem cells become smaller. The cell walls become thicker and they obtain a darker color. That's why each concentric circle inside a tree cookie exists as a light colored band and a dark colored band. One light colored band and dark colored band together constitutes one growing season. And we will count these concentric circles in order to determine the tree's age. And we're going to do so through the use of what's called an increment borer, a tool you'll be introduced to at a later time.